Good evening, everyone. In a few minutes, the Nintendo Hacking 2016 talk will start. This talk will be translated into German, and there are English subtitles available. Anyway, without much further ado, these are Derek, Neerweert, and Netwil. The three students have been working on hacking the Nintendo platform for a while now, and please give them a warm applause.
Hi guys. So we'll come to our talk about Nintendo Hacking 2016. Let me quickly introduce the other guys. This is Derek and that's Ned. And I think I can speak for all the three of us to say that I'm really happy that you guys are here today, and we are happy that we can be here today to tell you everything about what we did in the past 1.5 years, I guess. So I will start with the state of the Wii U. I hope a lot of you guys have seen Failoverflow's talk in 2013 about hacking the Wii U. Not much happened afterwards. Until 2015, there is a public WebKit exploit released. And about at this time, we started looking into the Wii U. And we wanted more access, right, than just user mode. Because there is also the kernel running on a PowerPC. And then there is this other ARM processor that runs iOS U. Also user mode and kernel mode. I'm not going to consider the user mode today, because I think the kernel exploits are just way more fun. So let's start with PowerPC kernel real quick. It has all standard basic security measures, though it doesn't have any ASLR, which makes our life easier. It has about 140 syscalls, and we can't really name them from start, right? Kind of need to reverse it, but there's a nice thing. So the Wii U uses this RPL mechanism for dynamic libraries, and there's this really nice library, it's called coreinit.rpl, and it contains a lot of syscall shims and symbol names, so we can name all the syscalls straight away without much hassle. And it's important to note that all the syscalls use a safe copy-in, copy-out mechanism to get data from the user space into the kernel space. So you start reversing each syscall, and you start looking for bugs. And what we came up with at first is what we call IO-controlled vhacks, or why indirections are hard. It's actually a bug in the IPCK driver submit request syscall. So what this syscall is used for is you want to submit requests from user mode to this other processor running, which I'm going to talk about later. And so you submit these kind of request structures, and the kernel uses copy-in to fetch the request structure from user mode into kernel mode, but there is a certain type of request structure which contains an indirection, like a second layer, right? And well, they just ignore that for the second level and hope for the best. So let's look at the relevant part. I'm really sorry I'm showing you this code here, but it's not much more than that. So there's something that's called iOS packet in the second line, which is kind of this request that we submit from user mode into kernel mode. And in the top line, there's this special request entry. So it contains a physical address, a buffer size, and a virtual address. And what we do from user mode is we submit it filled out with the virtual address and the size. And the kernel does this convenient thing for us to kind of change the virtual address to the physical address. So we can see it copies in this packet from user mode into kernel mode using the save mechanism, and then it goes through all the entries and fixes up the physical addresses for us. But we can see in this line that it doesn't use the save mechanism at all. It doesn't care about whatever address we put in there. So this gives us some kind of write primitive to wherever we want, basically. This looks hard to exploit, right? Because the write kind of is going through this conversation, but we actually only need 1 byte to exploit the kernel. And we do this by noting that this ki affective to physical conversion function actually returns 0 for any garbage input we get. And there's a pretty high chance of the input to the function to be garbage if we point it to any part inside kernel data. So the strategy here is that we go into the syscall handler address table, and we overwrite the last byte for one particular syscall handler, and we hope that the new address actually points to some usable gadget. So we hope for the best, basically. And the other important thing to note here is that our user mode code is running from what we call the JIT area. And what's really stupid is that the JIT area is actually executable from kernel mode for some reason. So that's nice too. Okay, let's look at the relevant structures. So this is the kernel, and we should read this from the bottom to the top. Okay, like in the last line in the bottom, we see this entry to KE loader call. And then we can look at the last byte there. It's hex F0. And what we will do now is overwrite this last byte with 0. And what happens is that now the syscall will actually point to this very usable gadget up there, where it loads this register R28 into the link register and just branches there. And the nice thing is that we control R28 from user mode, so this gives us a way to just jump anywhere, basically. So how do we exploit this? Well, we have our kmode function there. Then we just call IO control V to this shifted address. And from this point on, we have this nice syscall that just jumps to anywhere we want, and then we call it, basically, and this calls our kmode function. So the Wii U starts out with full 4 hearts, and this gives us PowerPC mode code execution. So we subtract 1 heart. It's quite nice, but we kind of need to go deeper. For that, let's look at the IOSU architecture. So IOSU is present as one big ELF file, and this includes the kernel and all the services. And it's running on the Starbuck. It has a hardware way to enforce no execute, and again, no ASLR, making our lives easier. And it's a microkernel design and has about 140 syscalls. So another thing to note is that the kernel spawns all the services as user mode processes. So before we can exploit the kernel, we actually have to exploit one of these user mode processes, which we did, but I'm not going to talk about. And to look into the kernel, we again reverse all of these syscalls and search for bugs. And what we came up with is called MQHex, or message queue hex. It contains another nice bug class that apparently never dies, integer overflows. And let's look at the code again. So there's this syscall, it's called create message queue. You pass it a buffer and the number of buffer entries. And what they assumed was that each buffer entry is 4 bytes. So when they check the address range, they just multiply the number of entries with 4 bytes. So does anyone see the integer overflow here? And the other nice thing is that they just use the number of entries for the maximum number of entries for the message queue. And our write primitive, again, is the send message syscall. So I told you about this hardware NX, right? So iOS should be enforcing that no executable memory is writable. And if you look at the kernel section flags, we actually see that kernel text is read execute and kernel data is read write. But these permissions are all lies, okay? So our exploit strategy, well, let's look at the relevant part of the IOSU kernel. So we see that kernel text starts at this lower address at hex 812. And conveniently for us, there is a syscall there. And the addresses before that are all valid. So we create a message queue starting at -8 bytes. And this magic hex 400 whatever 2 number. And from this point on, we just push 2 messages and an ARM instruction to branch R3. And what this does is it actually causes the start of the text section to be overwritten with branch to R3. And let's just look at the integer overflow, right? 4 times this value, truncated to 4 bytes, gives 8 bytes. So what the kernel thinks is that the message queue is only 8 bytes, but we can just push any messages we want. Okay? So this gives us iOS kernel mode execution. And the nice thing about this is that we actually have full control over the console now, right? So we can dump the console's OTP, which contains all the keys, except for boot 1, which we will coming back to later, because unfortunately the keys for boot 1 are locked out, as we've already seen. And Now we want to make everything persistent. So how do we do that? We find that title content is only verified at title install time, but never at boot time. Because at boot time, they only verify the title binary. So what you can do is you can actually start to mess with the metadata of titles and overwrite it. And what we did was to overwrite the ROM for a DS game, exploited the emulator, and got user mode code execution again. And another thing is the console contains this config file, which tells it to boot into which title to boot. So what you can do is you overwrite the title ID with your modified DS emulator title, and the next time you start up the console, it actually boots into the exploited game. And yeah, so this gives us persistent code execution and cold boot with full control over the console whatsoever. So game over.
So as we just saw, the kernels are like pretty broken, right? So what is missing? And I just copied this slide from Fail Overflow's talk. As you can see, we are using the same default theme for our slides. And basically, the boot 1 key, which is the second stage bootloader on Wii U, this key is still unknown, and they tried to get it somehow with some side channel attack thing, but I think it never worked. So it would be nice to get this key. And the first thing we did was to make a NAND tracer, so we can basically sniff all the traffic from between NAND and boot 1 to see what boot 1 reads from flash. And so we get some nice addresses, and we could compare this with the file system on this flash to see what file it is reading. And we also kind of messed around with some files on this file system, and we found out that boot 1 actually parses a file that is called system.xml. And I don't know, it doesn't really feel safe to parse an XML file in such a really early boot process. I mean, there's a lot of stuff that could go wrong. So we tried to attack this. We tried some client exploitation stuff, but yeah, unfortunately it didn't really work. So let's try something else. So there's boot 1, which of course boots this. Sorry, we've got boot 0, and this boots boot 1. And Fail Overflow found out that this boot 0, which is the boot ROM of the security processor, can be re-enabled again in virtual remote, and you can just dump it. So let's look at boot 0. Sorry. And we can see that it reads the boot 1 key from OTP, and then it logs out boot 1 key for error. And this happens really early. But it's basically kept in memory all the time until it's done, until it has launched a boot 1 or just panicked. So this means that we have to exploit boot 0 to get the boot 1 key. And unfortunately, boot 0 is pretty safe. It's kind of surprising because this is a Wii U. And basically, this gives us this question: how can you exploit something that has no bugs? So the answer is we have to introduce our own bugs. And we are doing this by using fault injection. And maybe you have heard of it already. It's basically you introduce an error into the device by glitching the clock or voltage, the reset line. You can also do electromagnetic fault injections. There are many ways. But basically what you want to get is a mutated instruction or an instruction skip or some corrupted registers. What you don't want is just a stupid lockup where it just crashes. And yeah, that's not really useful. So we want to glitch boot 0. And to do this, we have to find a nice target, like the weak spot of boot 0. So let's take a look what boot 0 does. The first thing it does is it copies itself to RAM for some unknown reason. I mean, there's no good reason to do this, but it's nice for us because it copies itself to RAM and just executes from there. And then it copies the boot 1 key to memory. It locks out the OTP slot, initializes some other stuff in Flash controller. And then it starts reading the boot 1 image. And it does that by just reading its header to this address. And then they read the size from the header field. And they also do some max size check on this. And please note, the header itself is not encrypted. And they also don't do any signature verification here at this step. So they use the size and read the whole boot 1 image using the size, and then they do real signature verification, make sure that the image is not corrupted. It then decrypts the boot 1 code using the key from RAM, and then it clears the key and jumps to the boot 1 entry point. Okay, so what is the weak spot here? And I mean, if you look at this, you can pretty much already tell what it is. And of course, it's this size check. So what we can do is we can write our own modified version of boot 1 to Flash with some really, really large size in the header. So it reads the header, and then it's supposed to do the size check. And this is exactly where we want to glitch it. And eventually, it will just skip the instruction or something else happens, and then basically the size check is bypassed. So when it's reading the boot 1 image using this size, it will actually overflow the buffer. And we have some jump instructions at the end. So when it returns from the flash read function, it will eventually jump to our code. And this is actually boot 0 code execution. Okay, so we have boot 0 code execution, and we can just dump the boot 1 key from RAM. And we didn't even need an exploit for this, right? So it's just boot 0 is actually pretty safe, right? But when it comes to glitching, it's kind of fragile because boot 0 code is writable, and also the boot 1 image buffer is in front of boot 0 buffer, so we can just overflow it. And also the setup that I had is surprisingly stable, so it works like 50% of the entire time. So let's finally look at boot 1. And boot 1 is able to understand the Wii U file system. It uses real file path strings to load the firmware image. And of course, the first thing we did was to look at the XML parser. And, well, unfortunately, it seems pretty safe. Yeah. But maybe we found a bug. We are not really sure, and we haven't really tried to exploit it. Interest kind of faded out because, it's, after all, it's just a Wii U. So that's it for Wii U, and now I will hand over to Netwill. He's talking about 3DS.
Hey everyone, I'm Ned. I started 3DS this year, and I'm basically a software person, so I'm going to be showing some of the homebrew side of 3DS, where that's at right now. So just to reiterate from last year, these guys broke userland kernel and security processor. They also broke the secret hardware key scrambler. And since then, Nintendo's been kind of mad about this. They released a lot of system updates. And they started a bug bounty program. So there's a lot of bugs getting patched, but because of the level of exploitation we got last year, it's actually really easy to find new bugs and new exploits. So what I want to emphasize here is that even though it's like a cat and mouse game, because we have so much control, we can exploit more difficult bugs on the latest firmware. So starting with user space, this is where all homebrew comes from. So already it's pretty good. Like, this has always been a huge focus for the homebrew community, because it's kind of where, user space is where you want to be running your own custom games, modifying stuff. So we have a bunch of game entry points and a bunch of browser exploits, but there's a couple limitations to these, and that's that game carts cost money, and they frequently are, like, the games that are exploited are usually somewhat rare and unusual, and so the price goes way up as demand soars. And for the browser, every time we release a new browser exploit, Nintendo can actually enforce that you're on the latest firmware, because before we fetch any web page, it'll check that the system's on the latest version. So they can kind of remotely cut off web browser exploits. So looking at this, I thought it might be fun to look at if any of the system titles could be exploitable as primary entry points. And I found something called sound hacks. So just the basic, like, the two probably most obvious things to look at are the image loader, because it's got JPEG parsing, and also the music player. But when I looked at the music player, I saw that they're parsing actually a lot of formats, and they even have their own custom playlist format. And if they make a single mistake anywhere, it's over. So then I was trying to compare with, like, open source implementations. I didn't find any overlap. It seemed like everything was custom, so that was pretty promising. So over the course of about a month, I found a bunch of bugs, and I was trying to, like, chain together little, like, logical bugs, and it wasn't really working. And then I just found one that was really critical. So I'm going to demonstrate that here. So I actually studied MP3 for, like, the whole month. MPEG was, like, the last day. So I looked at it, and they actually malloc 256-byte buffer for the song name. And then when they go to load it, if they see a Unicode bomb marker, they just memcopy the thing. And that tag size is totally controlled. So, that's it. So so this is pretty great, but it's a heap exploit, so it's a little tricky, but this is what it looks like. So we have our name chunk that we're about to overflow, and then, like, I'm a CTF player, so I just put A's there. And then the next thing that happens is this gets freed. And so this victim chunk that we've overridden, it's actually, the way the 3DS heap works, they actually track, they have a linked list of what things are currently allocated. So this gives us the classical heap on link arbitrary write. And so at this point, we have a 4-byte write, and we want to get ROP out of it. So we'll probably do a stack pivot. So I looked at the binary, and there's only one pivot gadget. And then I looked at the thumb pivots. There are actually a lot, but because this CPU was too old, it didn't support the wide instructions where all the pivots come up. So unfortunately, that one pivot instruction has some, like, arithmetic conditions on it. Specifically, it was that in order to load all your registers from memory, the the condition flags had to satisfy less than. And everywhere where we returned from the function, it had just checked that, like if this pointer is not null free, and so the comparisons wouldn't ever be satisfied because nothing's mapped up in the negative area. So, of course, CTF workarounds, we can still do this. So, overwrite the heap free list head with a stack address. And so on the next malloc, we just return that stack address and read into it. So there's a couple of constraints on this. And the first one's really normal. Like this is every pivot to stack heap thing. You have to make sure that you have a heap chunk on the stack. And luckily, this is actually pretty easy because all you need is a size followed by 2 null pointers representing next and previous. So when malloc goes to look there, it sees like this size is big enough, and then nothing else is in the queue, so we'll just return this. And then this worked. So we memcopy the next tag to the stack, and like we just specify that size, mallocs and reads it in for us, and then from there we're done because we can just do a little wrap chain where we memcopy the shellcode to the heap and then use an existing exploit, gspwn, which has been around for a long time, to overwrite the text section and jump there. So there's the first heart. So you can't really talk about homebrew without also talking about kernel because we want to get access to more syscalls. Like the 3DS actually sandboxes a lot of the syscalls away from you. And so as an attacker, well, your goal is to call some syscalls that are restricted. A really nice example would be you'd want to map some executable memory for like a JIT emulator. So it's kind of a tricky situation because you're inside the sandbox, you want to break out. You have to find bugs in like pretty restricted syscalls. So I looked at last year's talk here and like what had been done so far, and it seemed like there were a lot of attacks on that memory mapping. But I didn't see much about the sync primitives or anything related to use after free. And I had just got a pretty bad grade on my OS project because I had a lot of those. So I knew this is a good place to look. So I noticed a design flaw when I was reversing the ref counting. So it's not so much that they couldn't possibly get this right, but generally when you're designing an API, you want to make it really hard to abuse. And this is just not really true for how they do ref counting. So I'll go ahead and bring all these up. Yeah, so basically, whenever the user fetches a kernel object to perform some operation on it, meaning you call a syscall that does something using a kernel object, it does the correct incref and then decref for you. But I was looking at it and I was thinking, well, like a lot of times the kernel actually is using these objects internally to do stuff. So, I mean, I spoiled it, but like, I mean, it was like a week. I found like 3 use after frees, and they're all following the same pattern. The kernel is using an object internally without maintaining the reference count correctly. And then some people ask me like advice on kernel hacking, maybe like at home. I definitely recommend looking here. I'm sure that there's plenty more. So the one I'm going to talk about today is the timer object. So this is a pretty simple API with the kernel. You can have it create a timer for you. And you can set the timer, you can wait on it. It's like a normal synchronization primitive. So like I said, I was looking for these use after frees. I saw this and I thought it's kind of interesting that this one called pulse is here, because what's happening with this one is when you set the timer to pulse, like every period it's signaling everything that's waiting on it, and then it like resets itself, and then if you wait on it, the next period comes around, you signal again. And so I was thinking like it's definitely doing some stuff with this object internally that's like a bit more complicated than some of the other modes and the other kernel objects. So I looked at how they did the pulse, like, you know, every second, whatever, when it pulses, like what's actually getting executed. And if you look here, they do some pretty good locking, and then they signal. And then what happens here is basically when they signal, they go through and everyone that was waiting gets rescheduled, made runnable. And then at the end, they reset the timer state and just say like, okay, everyone that waits on this again has to wait for the next cycle. And then this also looks pretty good. Like they're locking the scheduler here. And this would work, but nothing's preventing you from just closing this from another core. So I have fast hacks, which is just 3 syscalls. That's it. That's the entire exploit. There's a lot of setup, which we'll get to. But you just create the timer, set it to run really fast, and then close the handle. And then if it was pulsing and you closed it, it'll use after free. So what's nice about this is if you lose the race, the timer is just unscheduled, you're fine. And then it actually happens quite often, and I didn't even really specifically try to win this too well. Like once it was within a second, I didn't worry, but those parameters are probably not optimal. So we should look at how do we exploit this. Basically, this is a little bit more complicated view of it. I'll show a diagram in a second. But this is like where the use after free actually happens. So like R7's pointing to my timer object, and then it was freed before we reached this chunk here. And then it's loading R7 to R0, loading something from that, and then branching to it. So that's like calling a use after free object. So this is pretty exploitable on the 3DS kernel because they use a slab heap to deal with allocating the objects. So this is the normal situation when that first timer is allocated. The vtable is pointing to the real ktimer vtable, and then it wants to call that timer reset function. It's totally fine, but when we free it, it actually that vtable pointer goes to the next freed timer object in the kernel. So it's actually interpreting that struct as a vtable. And what's nice is it actually overlaps with the initial timer value that we totally control. So it looks like, okay, we could just set the initial timer value, do this use after free, and we're just calling user space. That's what I thought, and then I realized it wasn't that easy. So because the race, because what's actually calling this is in a kernel thread, we actually can't guarantee that our user process is actually mapped in memory. And in fact, it's on a different core. So even if you open a process on the other core, like ran a thread there, you can't get more than 25% of the time, I think. So that's just super unstable. Also, because it's a kernel thread, we don't necessarily want to crash it. We don't like crashes in general, but this will just totally break everything if the timer sync thread dies. So as long as we return to a function, do something cleanly and return, it'll be fine. So it sounds like, okay, all we have to do is find some kernel function we can call, and we're done. But there's actually another issue, and that's that kernel code is mapped at high addresses, and these are actually negative. And the set timer syscall actually checks if your timer is negative. So there's a pretty funny trick I found, and it's that when you set the timer, you're saying start 1 second from now, start pulsing. Obviously, it's adding the current time to the 1 second to know when do I trigger this timer. So set timer is the one that does that add for you. They don't check for overflow when installing it, and timer schedule values are signed, which is also a bit weird. So we can overflow and schedule into the past. So how this looks is that's my disgusting setup call. So what's happening is in the middle, that's the start of the 3DS boot. And then that range on the right is what the 3DS will allow you to pass for your values for the initial and pulse period time. And so what I do is I just put it right there at the end, and then it overflows. And then on the next pulse, I also control that, and that's also less than that range. So then we can get it to line up on the kernel address that we want. And so That's pretty good. Unfortunately, we're at the end. Like at this point, it's pretty solid, but there isn't like an obvious single thing we can call. And it seems like, well, maybe you could race a bunch of times and call a bunch of different things in the kernel, and like, you know, that's a decent amount of control. But because of all this weird negative scheduling stuff, it's actually pretty hard to do multiple calls. So I was trying to look for one thing that I can call that will give me control. And this is where it gets really tricky. So if we look at how the memory mapping on 3DS works, in user space, you can access the FCRAM, which is that first range up there. That's just where your heap goes there. And then the kernel also has a view of this heap. It's a shared mapping, so if we can write one of those, something in that range, into the free pointer and allocate it, it actually ends up in something we can see as the user. So then I noticed this. This is actually a common instruction prefix in ARM. So I jumped here, and at this point, like we just did a C++ view table call on the useAfterFree thing with one argument. So this means that R0 contains the address of the object, and R1 contains the address of where we just jumped to. So that like B65C is where R1's pointing. So this is actually like some random linked list lookup function, but it's actually looking down to that add instruction and loading it to R1, and then we write that to the object. And so at this point, it looks like this. It's pointing to something in user space, and then we just alloc 2 times. We can look in user space, oh, they put the object there. You control the vtable, and from there, it's pretty much standard, straightforward thing. So there we go. Got full ARM11 user space and kernel. And this is almost game over. One more time.
So we have broken several parts of the 3DS firmware, including the 3DS kernel and all the software that's running on the security processor. What we haven't looked at yet are the 3DS boot ROMs. And basically there's one boot ROM for each processor, for the ARM11 and for the ARM9. And I think there's probably there are more boot ROMs in the 3DS system on a chip used for old Nintendo DS mode, but we will focus on the 3DS boot ROMs here. And what we know is they are somehow loading the firmware image from NAND flash. And we also know that the ARM9 boot ROM does all the interesting stuff, because only the ARM9 has access to the whole crypto hardware, like AES engine, RSA engine. We also know that the boot ROM will initialize the secret keys for the AES key slots. And yes, we would like to get those keys. But unfortunately, the boot ROM is disabled. It disables itself before it's launching the firmware. And 3DS boot ROMs also print nice error screens. Like when the NAND is corrupted or something, it shows an error screen. So let's look how the boot ROMs are protected in detail. Basically, there are 2 registers that we call config sysprot9 and sysprot11. And the boot ROM writes to those registers, and of course, they are one shot. You cannot re-enable the boot ROMs again, because this is not the Wii U. And basically, when it disables the boot ROM, it only disables 1/2 of it. So what you get are 2 parts of boot ROM. There's the unprotected part and the protected part. You can just dump the unprotected part by taking over ARM9 from firmware, but you can never see the protected part. And they were really clever, and basically they put all the interesting code in the protected part. And if you look at the reset vector, it just jumps directly to the protected part of the boot ROM. So you can't really figure out what is going on when the 3DS is starting up. But what you can do is, you can look at the code from the unprotected boot ROM, and who knows, maybe we can find a bug. So let's do this. First of all, of course, there are no keys in the unprotected boot ROM. They put all the keys in the protected part. It's also mainly, it's a lot of driver code. It talks to some hardware like NAND flash, MMC, the AES engine, and also to a SPI flash, which is kind of interesting because the SPI flash is some really tiny chip that is soldered on the Wi-Fi socket. And it's actually used for some Wi-Fi settings and other user settings used by old Nintendo DS mode. And yeah, that's kind of interesting. It uses this SPI flash. And it also includes the ARM exception vector table. And this is actually a design that they have adopted from previous generations of the Nintendo DS, such as the DSi. If you don't know ARM, basically you have something that is called an exception vector table. And this is located at this hard-coded address in boot ROM. And basically, every time when something weird happens or something special on the CPU, it will jump to those exception vectors. Like the reset vector that we just saw, or when you're trying to read from an invalid address, it will jump to the prefetch abort or data abort vector. And also when you receive an interrupt, it will jump to the interrupt request vector. So those are the exception vectors, and they are hard-coded in the boot ROM, and there's kind of a problem with that, because as a developer, you don't want to put the exception handler routines in the boot ROM. You want to be able to change the code, right? So what they do is they just redirect all the exception execution flow from boot ROM to another jump table that is located in ARM9 memory. So it looks like this. What you can see here, the boot ROM vectors, it's basically just a jump instruction to the RAM vectors, and the RAM vectors are also just another jump instruction to the actual firmware handler. And this is how things look like when the firmware is running. But what about cold boot? Well, on cold boot, you get this. And this looks kind of interesting because you have the boot ROM vectors that still point to ARM9 memory. But since this is cold boot, the RAM is not initialized. So this is interesting, but it's not really a bug, because at some point, the boot ROM will initialize those RAM vectors. So, but let's cheat a little bit here and say, let's just assume we could somehow trigger a really early exception, even before the boot ROM is able to initialize the RAM vectors. Well, probably it would just crash, because on an exception, it would just jump to uninitialized memory, and there's probably no valid instruction there. So this is not very useful, but there's a really nice hardware flaw, and we found this by just writing to some memory reboot and see what happened. And basically, we found out that some RAM is actually not cleared on reboot. And this also includes ARM9. So the basic idea is we can set up some custom exception vectors in RAM that redirect execution flow to some dumper code. So when we reboot, we get this. And this is really interesting, because if you look at this, this means all we need to do now is trigger a really early exception, and then the boot ROM will jump to our dumper code. So how can we trigger an exception? Well, if you look at the exception vector table again, there are some exceptions that we can trigger, like because they are hard-coded, like reset, and they won't jump to online memory. And you also can't use the interrupt vector because interrupts are disabled on reset, and yeah, this won't work. So what is left is these three interesting exceptions. And if you look at those, they normally don't happen, right? Undefined instruction is really rare, and it shouldn't happen. So I don't know, but this reminds me kind of like it's a really nice use case for doing fault injection again, because you can corrupt registers and get mutated instructions. So it's really likely that it will trigger an exception. So this is the vector glitch hack. Basically, we set up some vectors in RAM, trigger reboot, then do some glitching magic, and then we reset again and let it boot up normally. And hopefully, the dumper code got executed and just wrote a copy of the boot ROM in memory, so we can just dump it. All this stuff is not very stable, but it works for me. So, okay, we got the boot ROM, and Nintendo's losing a life there. So, before we look at the boot ROM, I have a little prologue for you. And basically, in early 2014, an FCC document became public. There it is. And basically, it says that Nintendo has changed the CPU of the Nintendo 2DS. And there's one really interesting sentence that basically says they've changed the security function of the initial program loader that is installed in each model. So the initial program loader is probably the boot ROM, so obviously there must be some really huge bug in the boot ROM, right? So let's look at the boot ROM. Basically, there are some boot methods. You can boot from NAND, that's what it normally does, but alternatively, you can also boot from SPI Flash, which is a Wi-Fi flash, and it will only boot firmware images that are signed and encrypted. There's no freaky development backdoor that we can exploit. It also uses two different set of keys for NAND and non-NAND boot methods, and also for retail in dev mode. So even when stuff gets leaked, you cannot use it on your retail console. So let's do a small boot walkthrough. It's pretty straightforward, actually. So the first thing it does is it selects a boot device, then it loads the firmware header and the RSA signature from it. It's just one block. And then it hashes the header and extracts the hash from the signature and compares it. So basically, basic signature verification, header verification. And then it assumes, the header is safe, and then it starts loading the firmware sections. And the firmware image is a pretty simple format. Like you have some entries in the header that tells you, okay, take the data from this offset, and there's a section with this size loaded to that address. It's pretty simple. So we know from Nintendo's past that they like to mess up RSA signature checks. So let's look at how RSA is done on 3DS. So for the 3DS firmware, they're using RSA signatures in the PKCS standard. PKCS is basically a bunch of standards that tell you how your signatures have to look like. And they are using the 2048-bit version of RSA, which is safe. And in the signature, you have the SHA-2 hash. And this is encoded using ASN1. And ASN1, it's some really complex structure. It's basically, it's similar to the MP3 structure. So you have little chunks of data, and those chunks have little headers, and the headers have tag bytes and length bytes. And basically, this ASN1 stuff is used to tell the parser which hashing algorithm is used. And, well, since the SHA-2 hash is only 20 hex bytes in size, you have some remaining space in the signature that you have to fill. And PKACS says you need a padding, and this padding should be deterministic. It should only contain FF bytes. So when you're trying to forge signatures, it's really difficult because of this padding that is really long. And when you compare the signatures of different firmware images, you will actually notice that only the hash will change. The rest of the data is always the same for all signatures. But, well, for some reason, they decided to write a signature parser for this stuff. So what you get now is, I would say, the Nintendo way again. So the first thing it does is it tries to parse the padding, and this parser is totally messed up. Like, there's a flag byte that tells you if the padding should be checked. And if it's 1, then it is checked. It should be all FF bytes. But if it's 2, then it will just skip the padding. And it also has some really weak bounds checking. It makes sure that it will not, when it is passing the padding, it makes sure that it will not go out of bounds. But they forget to verify that the hash will actually fit in there as well. So the next thing they do is parsing this really complicated ASN1 structure. And this parser is also really simplified. So we know ASN1 has some length fields, and there's no bounds checking. So eventually it will add the length to the current pointer in the signature. And then they stop parsing and say, okay, we parsed all the data, and now there should be the hash. And yeah, they are not checking this length. And this pointer is used to do the hash comparison. So all in all, you can say it only checks a few bytes in the signature because the padding parser is messed up, and also the ASM1 parser is really simplified. So what we can do is we can brute force a perfect signature where the final pointer, when it's done parsing the padding and the ASM1 data, that this final pointer matches the pointer of the calculated hash of the boot ROM. So what it does then is it does a mem copy, a mem compare with the calculated hash and the calculated hash. Like, and this never fails, right? So it will always succeed, and this is SIG hacks. So SIGHAX is a boot ROM exploit for 3DS. And basically, we can sign our own firmwares. And there are over 60 million vulnerable devices. Basically, in a new 3DS and 2DS, basically all models are affected. And of course, since this is the boot ROM, Nintendo can't fix it. So that's pretty nice. But there's one heart remaining. So something is missing. What we haven't done yet is we haven't dumped the ARM11 boot ROM. It's probably not really interesting, but for the sake of completeness, we would like to get it. And In theory, we can just do a vector glitch hack again, because it has the same flaw. But now that we can sign our own firmwares, let's try something else. So if you look at the unprotected part of the ARM11 boot ROM, you can see there are a lot of references to ARM11 memory. So maybe now that we can sign our own firmwares and we can set up our own firmware sections, maybe we can overwrite some boot ROM data. So, but the boot ROM developers were kind of clever, and the ARM9 boot ROM checks the firmware sections, and they have some kind of blacklist. And unfortunately, you can't just overwrite boot 9 data sections. But for some reason, they forgot to blacklist all the boot 11 data regions. So you can just overwrite boot 11 stack or the exception vectors, and well, you can dump the ARM11 boot ROM. Yeah, that was pretty easy. And now I get to tell you something. All this stuff about the boot ROM, we did this in summer 2015. So we could have talked about this already last year. But since we are kind of friendly hackers, we hold this bug so long. So yeah, Nintendo should be thankful. And okay, so that's it. 3DS free, game over. And here's a picture of Nintendo Switch, and our buddy is already.
Thank you very much. There's about 5 minutes left for questions. Are there any questions from the internet?
Oh,
None?
hello. Okay. Yes, there's actually one question from the internet, and that is, the internet wants to know if we can get DSP code execution maybe sometime soon.
Can you repeat the question?
Yeah.
It's very hard to understand here.
Okay. The internet wants to know if we can get DSP code execution.
Well, the DSP of the 3DS runs its own firmware, and that is included in some kernel module. And basically, when you can sign your own firmware, you can also make it load another DSP firmware. So yes, you can do this.
Okay, people who are leaving, please do so quietly, and people entering also please do so quietly. There was a question on microphone 3, I think, but no longer. Okay. Does the internet have more questions?
Yes, it does. The internet wants to know if you or how you glitched the Wii U to get execution.
Well, I don't want to reveal how I did it in detail, but there are some basic fault injection attacks, and my setup was, I think, kind of complicated. You had to modify a lot of stuff on the Wii U mainboard to get it work. So I guess you have to figure it out yourself. Sorry.
Okay, there's a question upstairs, microphone 5, I think.
7, but it's okay. Yeah, well, you said that you broke all the 2DS, but actually you showed that the 2DS changed in the boot process. So did you verify that that worked for the first version as well?
Yes. So the new 3DS was released after the 2DS, and the new 3DS is also vulnerable. And basically, all the Nintendo 2DS consoles are also vulnerable as well. Yes, we did verify this, and we don't really know what this FCC document is about. we got some really new 2DS from the store. And basically there's no difference for the boot ROM at all. So yes, everything is vulnerable.
Nice to know. Thanks.
Okay.
Final question for microphone 3.
Yeah, just a fun question out of interest. When you're going to buy such a device, do you also plan to play game on it? Or is it just going to check if how the kernel works?
Personally, for the Wii U, I own 0 games, so...
Great, thanks.
I also didn't pirate any, so I never played a game on my Wii U.